So we look at tutorial 3. In this tutorial 3, we only have 4 questions. Okay, our friend. I'm not sure the version that you received, whether is this the version. Okay, if this is a version, please cancel off question number 5. Okay, question number 5 is actually based on this lecture 5. That is on the traffic survey, right? Last time we did use this moving observer method to actually calculate the speed and also calculate the volume of the traffic on the road. But nowadays we don't use this type of method anymore. Okay, the more frequent method that we use is that you stand along the roads and then you count the number of vehicles. Okay, very few we use this moving observer. Moving observer means that you go inside a car, you drive a car. Okay, you drive a car on the road and then you count the number of vehicles in front of you, and also you count the number of vehicles passing by you in the same direction and the opposite direction. Okay, so it's a bit complicated in that sense, and now we don't use this method anymore. Okay, so we just leave it for question 5. Okay, question 1 to 4 is about the transport planning. Okay, question 1 is on traffic generation, or we say trip generation. The authority is planning to develop a new town in Kajang. Table Q2 shows the planned facility in the town. So as the planning engineer in the authority department, you have to estimate the trip generated or attracted to this new town, given the following table for your reference. Okay, so this question tests you whether you know how to match the type of development into the types that is we got from the manual. So we assume that this is what we have from the manual, and this is trip rates. Okay, we know we can have many methods, right, to estimate. We can use a regression, we can use cross classification, but this we use the trip rates. Okay, so for double story houses, we refer it to the residential. 2.5 story houses is also residential. The shops is we assume retail, and shopping plaza we assume retail. Okay, you may ask me that, you know, in the shopping plaza we may have the service as well, but we have to look at the overall how much is the percentage, right? So if let's say you have 100 shops, okay, in your shopping plaza, and among them 60 or 70 is actually retail. Okay, 40 is or maybe up to 70, that means you have 30 which is service. So we take the majority, we use the retail. Okay, so in this case, because there is no perfect manual in the world, because somehow we will have some that is not really inside our manual. Like in Malaysia, also the same. We have the mixed development, right? So the mixed development is not in our manual. If you see the trip gen, we have commercial, we have residential, but we don't have mixed development. So sometimes we may need a little bit of this, what to say, our judgment. Okay, we need to have that. Okay. Okay, so from here we got enough. Okay, so here is that we have the number of the size of the development, which is 1000 square meter. Okay, times 600 times 300. Then after that we have here 600 times 25.8, because residential is 25.8 per 1000 square feet meter, and now we have 600,000 square feet meter, so we times 600. Right, 2.5 story house, we have 300, shops we have 100, shopping plaza we have 100 using the 87.7. So this is the trips that will be expected to be generated, okay, from this town area, and this is the total value. Okay, so this is how we use the manual, okay, to calculate that. This one is only one-sided now, generated or attracted, okay? Because if you look at our manual, we have in and we have out, which is generated or attracted. In this case, it's just general. We either are calculating in or we are calculating out. Okay, there is no specific mention, okay, which type we are calculating. Okay, because the question say here, right? Generated or attracted. Okay. Any question? Okay, so now we move to question number 2. All right. So question number 2 is on the mood choice. A group of lecturers in Utah have agreed to stop commuting by motor vehicle. Instead, each of these teachers will choose each morning between walking and bicycling to school, depending on the weather. The utility functions for the two non-motorized modes are given. This is the utility for biking. This is the utility for walking. Okay, where W is a weather-related variable and T is the travel time. W is 0 if good weather, W is 1 if it is bad weather. Okay, when the weather is good, what is the probability that a non-motorized teacher with a choice between a 15-minute walk and 6-minute walk will bike ride will choose the bicycle mode? Okay, so weather is good, W is 0, so this term will cancel off. We only have 0.2, okay, so these two. We wanted to know how much is the probability. Walking, 15 minutes, right? Biking, 6 minutes, okay? So you plug in these equations, this is what you got. So you got the utility for biking, you got the utility for walking. Then you calculate the probability of biking and walking based on the logic model. So you calculated. For biking, you get 86%. For walking, you get 14%. Okay? So this is what you have. Right? Okay, then part B. At what value of the weather coefficient, C3, okay, will the teacher in part A be equally likely to choose walk and bicycle in bad weather? So in bad weather, W is 1. Okay, so W is 1. You wanted to know how much is the value of C3. Okay, W is 1. You want to know how much is the C3. So they say that, okay, this is equally likely. So equally likely means that your utility is the same. U bike will be equal to U walk. Okay, so here this is what you get. Okay, U bike equals to the U walk, and then you make these two equations equal, you get C3 is 1.8. All right, any question? Okay, so far so good. Okay, we'll move to next question. That is question 3. Question 3 is on traffic assignment. An origin destination pair is connected by a road with a performance function, right? Is given T1 is 8 plus x1, T2 is 1 plus 2x2. So we wanted to know at equilibrium, at user equilibrium, okay, what will be the road travel time and the total travel time. So we have two unknown here, right? One unknown is x1, another unknown is x2. And according to the Watt-Rod principle user equilibrium, okay, T1 is equal to T2 at equilibrium. Okay, that is very important for us to know about that lah. Okay, how is it? Okay, T1 equals to T2 at equilibrium. And based on the flow conservation equation, okay, x1 plus x2 is equal to Q. Q here is given in the question already. It's 4,000 vehicle per hour. Okay, so your Q is 4,000. So x1 and x2 add up. This is what we call flow conservation equation, right? So you have two unknown. You have two equations, you can solve it. You solve the equation, you get x1 is this, okay, x2 is this. Okay, so, and then you plug in, you got your travel time. Your travel time for road 1 and road 2 is the same, okay, because this is our assumption, right? This is our input. If you got it differently, that means you are wrong, okay, you have to check back, okay. So, because at user equilibrium, any of the used road, at least one person is using that road. That means the travel time on that road will be the same as all other used roads. Okay. And finally, we want to know the total travel time. Total travel time means that for each of the driver on the network, okay, each of them, the 333 people, right? Each of them, they will need to experience 8.33 minutes. Okay, so you have total here, how many? So in this case, this one is also meaning that here, this one, right? This one we also mean is like that. You have x1 plus x2, okay? And then we times together with t, okay? It can be either t1 or t2 is the same, okay? So here means that you'll have 4,000 times with 8.33. Right? So your answer is 33333. This is in the vehicle minute. Okay, vehicle dash minute means that you add up the minutes, the minutes waiting time for each, or we say the travel time for each of the driver. Okay, for a total of 4,000 people. Okay, any question for question 3? Okay, no question? All right. So we move forward to question number 4. A new expressway has a link performance function of 6.1 plus 3.3 Vx, where Vx is the traffic flow volume on the expressway. And then we have the TA equals to 8.2 plus 17 VA, where VA is the traffic flow in the arterial street. So we wanted to know if all drivers from zone 3 to zone 1 want to minimize their individual travel times, at what true flow rate will the drivers begin to divert back to the arterial road? So here, this is the two roads that we have, okay? So here, this is the travel time, okay? And then this is the volume, okay? So we know this volume. Okay, our next question, which one is our TX? Which one is our VX? Okay, so this should be our TX, TA. This should be our TA. That means on the arterial road. Okay, this is on the arterial road, and then this is on the expressway, right? Because we see the time at the free flow. Okay, time at the free flow. If TX is 0, okay, if TX is 0, I mean, if volume is 0, the free flow time for this TX is lower as compared to the arterial stream. Okay, so that is how we differentiate, okay, TX and TA. All right. So here you can see, okay, the free flow travel time on TA is 8.2, right? Given the question here, we have 8.2, right? 8.2 for TA, and for the VX is 6.1. So at first, when you are the first driver to choose these two systems, okay, at first you will choose the expressway because the travel time is lower. Then when more and more people choose the highway or expressway, the travel time will increase, right? And at one time, this travel time will equal to the 8.2. So this is the volume that we wanted to know. How much starting from here? Okay, then people will start to divert to the arterial. Okay, so the solution here you can see, right? When your travel time on the expressway is equal to the free flow travel time for the arterial streams, then you will get this. Okay, 636.36. So that means if you are the number 637 driver in the system, you will start to choose arterial stream. So when you choose the arterial stream, the travel time will increase. So the next driver will have to choose, see whether your expressway is faster or the arterial is faster. Okay, then they will assign accordingly. All right. So at the end of the day, at the equilibrium in the question B here, so at the question B here, we know that a total of 2261 vehicle per hour, okay, is going to flow between the 3 and 1, zone 3 and 1. Okay, so it means here that, okay, Vx plus Va will equal to 2265, and the travel time on these two roads will be the same. This is following the one route principle. Okay, and we solve this, we got Va 277 and Vx 1988. That means at the end of the day, at the equilibrium condition, okay, we will have more traffic on the expressway rather than on the arterial road. But the travel time on these two roads, whether expressway or arterial road, the driver who are experiencing the travel time on the road will be the same at the equilibrium. Okay, so that is for question 4. Any question? Okay, so if no question, so you are now expected to start doing your tutorial question, right? I have already explained all. If you haven't do it yet, then you can start to do it. So that's all we wanted to discuss.